So let's just see what it said here, right? If it's right, so what we know about diffraction, right? Once a wave goes through an opening that is small enough, it will spread the waves out. If the opening too big, it will spread out much. Okay, so let's see what this person says about it, right? If a slit is placed in the path of a parallel beam of light, most of the light passes through the slit without changing direction. That is, in a manner which is consistent with the idea that light travels in straight lines. However, careful observation of the situation reveals that some of the light spreads into regions which would be in shadow of which would be in shadow if light traveled only in straight lines. If the slit is wide, the spreading is so slight that it can normally be ignored. That's okay. If the opening too big, the light goes through, nothing already happened. All right. But if the width of the slit is comparable with the wavelength, right? So I know you're not really making notes, but it's like those little things, they make a note of that. In diffraction, if the width of the slit is comparable with the wavelength of light, then the effect is quite pronounced. The spreading of the light is called diffraction. So in your little notes, that's the first thing you should write, right? Diffraction, spreading of light, and it's more pronounced if, right? And it's more pronounced if the width is comparable with the wavelength, right? Making little notes as I go along. I'll try to underline the important things there, right? Right, another example of the effect occurs when light falls on small opaque discs. The light bends around the disc. The light bends around the disc and produces brightness. The light bends around the disc and produces brightness at the center of the geometrical shadow. Right, so basically, where you're supposed to have a shadow, you get light, right? All types of wave motion exhibit diffraction effects. It is a common experience, for example, that sound waves spread around components, right? It's all these things we know already from component, right? Diffraction can be accounted for on the basis of Huygens construction, right? In chapter 24, and I'm going to go through that. Anyway, right? We accounted for the propagation of wavefronts by considering that each point on the wavefront emits secondary wavelets, and by regarding that the new position of the wavefront as being along the line, which is the common tangent to the secondary wavelets, right? So that's something confusing. I want to show you this little diagram here. Right, go to chapter 24. I'll tell you what page that's on. If you look at page 428, right? If you look at page 428, we need to understand the basis of Huygens's construction, right? So whenever you see a big wavefront like this, whenever you see a big wavefront like that, that wavefront is basically made up of all these little secondary sources here. Okay, that's the principle that Huygens came up with. So let's take a look at Huygens, right? We'll have a page 428. Yeah. So if the present position of a wavefront is known, then Huygens construction enables us to determine what its position will be at some later time. It can be used for all types of wave motion, but finds particular application in solving problems in physical optics. In geometrical optics, the location of the image position, etc., can usually be accomplished more easily by making use of the ray diagrams. Right? So all the saying there is when I talk about lenses, just use basic ray diagrams, right? But try and focus here. Right here, try and focus on this part. We'll call us I want to explain it. Huygens postulated that each point on a wavefront could be regarded as being a secondary source. All right, so watch it here. Right, let me read that please. Right, as being a secondary source of spherical wavelets, and that the new wavefront is the surface which touches all the secondary wavelets. So watch this here. This is your wavefront, right? Picture the wavefront as producing a whole set of secondary wavelets. You're seeing that? So at this point, we have a wavelet. At this point, we have a wavelet. At this point, we have a wavelet. And so on, right? Yeah. Here's what Huygens said. Huygens said that the second wave, that's this wave in front of it, is basically the surface of all of these secondary wavelets combined. You see that? So if you take the surface of all the secondary wavelets and combine them, you will get the wave in front. That's okay? So he said that this one wavefront that we see it made up of a large amount of secondary wavelets. That's okay? It's not one wave, it's basically one wave producing the secondary that produces the one that is seen after. Okay, you can visualize that. All right. Again, which one there is the original wavefront? The one in front or the one behind? This one, wave one or wave two? Wave one. Wave one is the original, and as a result of that producing secondary wavefronts, you get the new wavefront in front. It's the second one. That's okay. Right. So Huygens postulated that each point in the wavefront can be regarded as being a secondary source of spherical wavelets, and that the new wavefront is a surface which touches all the secondary wavelets. So, right up, right, probably the first time you would have spent time on Huygens. Although Huygens only formed 5 syllables. I don't think I did Huygens. So you'll notice on that small diagram there that the new wavefront is basically a common tangent of all of them. You see that? Of course, they only have like 4 in this diagram, but imagine you have a large amount, right? That tangent will produce that nice smooth wavefront. Everybody okay with that? If they ask you to describe Huygens principle, you have to be able to state that, right? And obviously, catch that little diagram. All right, let's see how Huygens up for your choice. Let's get that ready. I'm about taking everything. Okay. Make sure it's getting. And we'll take a picture and your food. Right, let's take a look at the fraction of water. Wait, it's an example, right? I think it's a few pages down. I think here's page, I don't know. Page 434. Right, page 434 now, right? So when they talk about secondary waves now, and they talk about tangent and the new wavefront, you understand too, right? Right, Annalise? May I come back and explain this after lunch? And frontier, and I recorded it. And a little snippet and send to your mother. Right? Let's take a look at page 434. Diffraction is discussed in chapter 24, right? The phenomenon can be demonstrated using waterways in a ripple tank. And it illustrates what happens on this diagram here, right? You'll go to the diagram that's now. The width of the graph is small compared to the wavelength, and there is considerable sideways spreading. That is considerable diffraction. In figure 24.1, the graph is much larger than the wavelength, and there's little diffraction. Most of the energy associated with the waves is propagated in the same direction. Thus, the greater the ratio of wavelength to the gap, the greater the spreading. Right, here's what I put on number. Huygens construction, and in the meantime, glance across at page 435, right? Huygens construction can be used to predict the shapes of the wavefronts in figure 24.1. Right, it illustrates this for case 24.1. Note that though the construction accounts for the shape, it doesn't account for the reduced amplitude in the direction, right? So what you did, right? If you look at the diagram C, it shows you points A, B, C, D, E, F, G, and it shows you how the shape ends up like that. You see that? All those waves, they take a tangent of all those waves, and they end up with the curve. That's okay? All right, so now we're going back. Let's go back to where we were. Page 4. Back to page 450. I have to put it back right here, right? Chapter 24, the extensive wavefront, in which it can be shown that this is the only line which superimposed on the secondary, which does not cause them to destroy each other. All right, so you're seeing that the secondary wavelength produces it, right? And it doesn't destroy each other. Okay. However, if a wavefront is limited in some way, there are additional lines where complete destruction does not occur. These lines also represent the position of the wavefronts. These additional wavefronts account for the spreading that occurs when an extended wavefront meets an obstruction and becomes limited. we now have a formal definition of diffraction. So this is the definition that we're going to use at your level. Diffraction occurs as a result of the superposition of secondary wavelets from a continuous section of wavefront that has been limited by an aperture or opening. Okay, so this explanation includes the Huygens principle explanation. If they ask it in table definition, this is the one that you will get. Okay, write that one down. That's the most important definition. Right, and it's shown by the last diagram that we just looked at, right? Right, some of these things hard to envision, you know, this, so let's see if we can get a little video now. I don't know if you're seeing it yet with the wavefront, right? So watch this here. Let's watch a small video. Let's get that again. Alright, this should be a nice one, should be too long, you know.
This lecture is about to fraction and Huygens principle. Huygens principle states that every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. This can be a little strange, but I think it'll start to make sense if I give you a kind of visual example. So first of all, what does this principle mean by a center of disturbance? Well, a center of disturbance is a kind of center from which disturbances are radiating outward in all directions. An example would be if you throw a stone into a pond. The place where the stone enters the water is a center of disturbance, and waves spread out in all directions from that one point of disturbance. So as an example, if this red dot is a center of disturbance, waves are going to radiate out in all directions like this. So Huygens principle says that every point of an advancing wavefront is a new center of disturbance from which emanate independent waves in all directions. So what that
makes sense? Oh, you guys see that? No? That's exactly what I now told you, right? This wave produces the secondary wavefronts with this wave. This produces the secondary wavelets for this one, and so on and so on. So for example, if this is produced first, this will produce the secondary wavelets for this one, and then this one, and the wave moves outwards. Right? That's what he's saying, right? Hope you give us a good visualization.
What it means is that if we choose any one point on this advancing wave, it behaves like a center of disturbance. So it shows that point in the middle, and we can have a new wave radiating out in all directions. I've given this new wave the same wavelength as all the other waves in this wavefront. So you can see it has that same wavelength. So this is a little strange because if we're imagining this wavefront moving forward, there's no reason why it would suddenly radiate into a circle. And the reason why it's not doing that is that that one point is just one point on the wavefront. And what Huygens' principle is saying is that every single point along that line is behaving like a new center of disturbance. So I could put more points here and draw the waves radiating off of them because they are centers of disturbances, and I could add more and more. And you can start to see a pattern where there's one very specific spot where all of these waves are overlapping, and that's going to be right here. So that's where the next wavefront occurs. So what Huygens' principle is saying basically is that if you take every single point in a kind of straight line wave and model it as a center of disturbance, the waves radiating from all those centers of disturbance perfectly cancel out to make the shape of the wave that you're trying to predict. So here that's just going to be another straight line. That's where the next wavefront will occur. So why do we care about this idea? Well, this can help us predict how waves will interact when they hit barriers. When waves of light pass through a small opening in a barrier and as a result radiate out in all directions on the other side, we call this diffraction. This is a result of Huygens' principle. Every part of the wavefront would spread out in all directions, but most of the wavefront is blocked by the material, so the part that can spread out is not interfered with as it spreads. So we can imagine this wavefront approaching the solid barrier. And when it hits the solid barrier, most of the wave is not able to move through the barrier. The only part that it's going to be able to is the small point in the center. And I know that every single point along that line is behaving like a center of disturbance. So that means that on the other side of this barrier, the wave is going to radiate out in all directions like this. So this is how the wave is going to behave when it moves through a very small opening. It's going to change from all moving together as one kind of solid front to spreading out in all directions like this. So this is what happens during diffraction. When a wave of light passes through a small opening in a barrier and as a result it radiates outward in all directions on the other side. We can use Huygens' principle to predict the diffraction pattern for different shapes of barriers. To use Huygens' principle to predict diffraction patterns, we're going to start by drawing points on the wavefront only where it is not making contact with the barrier. Each point will be a center of disturbance. These points can only propagate when they're not up against a barrier. So I'm only going to draw points where there's no barrier. Next, draw circles around each center of disturbance. The circle's radius should be exactly one wavelength. So if I draw those circles, this is what that looks like. Next, we're going to draw a new wavefront along the circles meet in constructive interference. So that's going to look like this. That's where all the circles are meeting together in constructive interference and not being canceled out by other waves. So this is what the new line of the wavefront will look like as it moves through the barrier. This kind of makes sense if we imagine water impacting a barrier. We would imagine on the other side, the water would kind of begin to spread out back toward the center like this. We can then repeat this process to find the next wavefront. If I were to draw more dots along those lines and draw circles around them, this is what the next wavefront would look like. And then this one would be the one after that. So the wave kind of returns to normal after a certain amount of distance. We can observe the same barrier, but now with a longer wavelength. So I'm making bigger circles now because the wavelength is longer. And when I do that, this is the next line of the wavefront. There's one diffraction pattern that produces important and predictable properties, the double slit pattern. We're going to discuss this more in the next lecture, but this is what occurs when two small openings are made that the wave can move through. When this happens, this is how they radiate out. And you can see that there are going to be certain points of constructive and destructive interference. We're going to talk about that later in a separate video called the double slit experiment.
Okay, so let me show now.
This is the first lecture in a 2-lecture series on the double slit diffraction equation. In this first lecture, I'm going
looking for real life. See if I can go and get one.
This lecture is about diffraction and
But let's see if this is it, right?
If you shine a parallel rays of light on a cardboard with a tiny hole in between, what do you expect to happen to this light? I'm going to introduce this important thing that we saw about the wavefronts. Let's say we have a light bulb giving us light, and so what does the principle say? We're going to like
That's not looking for. If actual video showing it, most of them doing the one. Alright, nice. But you'll kind of see how the wavefronts are produced, right? Alright. Let's go back here now. Have a little idea of what it will look like. Right, so we have a formal definition. Ignore the next side, right? That's cranking up a diffraction that are not important for you, right? Let's go to 26.4 on page 252. Now doing this important part because the 26.4. Right, 26.4 on page 452. 452. Everything is 4. Everything is on 4. I keep making a mistake. Everything is on 4. Oh, yeah. These things are hard to visualize if you do understand something. Okay, these things are difficult to visualize. Like they are secretly rules, right? Okay, all right. So let's see what they say in this. So a typical single slit diffraction pattern, such as right, a single slit diffraction pattern such as that which might be produced by the arrangement on 26.1. That's what we looked at earlier, right? Right, is shown on figure 26.48. Take a little glance at it. Right, if you look there, that's what it'll look like. You'll see a central bright, then two little dark, then a bright again, then a dark again. You'll recognize that the further away you go from the central, it's not bright. Right. So if you look at the graph right underneath, it shows intensity. So the highest intensity is in the middle. You'll see that? And then it goes to dark. So watch the diagram here, right? But what this said is this is what you will observe. And the graph shows what will happen. So here's the highest intensity, so you're seeing that there. That's in the middle. Next state, you have dark, there's no intensity, that's right here. You're seeing that? Next state, there's bright, but that bright, the intensity is smaller. Right? Then there's a dark again, then a bright again. So there's a dark at Y, and then right here, you see bright again. So you recognize the intensity getting a little bit smaller and smaller. You okay with that? Yeah, you might just see it here, but beyond a particular point, nothing will happen. Beyond a particular point, there will be no more diffraction grating. Okay? So therefore, those little bars will only continue for a point in time. All right? So we will try to see why that happened. Right? So going back to the little note there. Right? The pattern can be accounted for by considering the superposition of the secondary wavelets, which are imagined to be emitted by each point on the wavefront between A and B. Talk about that already, right? A complete analysis of the situation is beyond the scope of the work. Right? Derive an expression, but we shall derive an expression which gives the angular positions of the minima and account for the central maximum. Right? So when they talk about I think I should be able to switch, right? So we're going to get an expression for what happens at that central point there, where the intensity is the highest, and all the other minimum. That's okay? All right. right? See, there are some values there, we're gonna go through that, right? Take a 2-minute breather. That's a lot that we're gonna go here. You want to go to the bathroom, go quick. Right? If not, you can take a minute and you can read up on the minimum. Here's the challenging part, right? This is what we have to understand properly. Right? That my note doesn't have this diagram. That's not using this. Okay, this is very important, right? Because sometimes they ask to explain how the diffraction rating pattern is on. Yeah, but I want you to digest constructive and passive functions too, right? This is the one that we're going to put it up. Oh, but there's more in the graph. Wait, what we'll explain that. This is something different. And the fraction rating is not like in the parents, the double set. Much smaller. So imagine 1 centimeter about 1,000 slips. That's how small the slips are. How about with microwave? I only go to the breakdown. How about microwave? That's up and take all the fraction. There is one, if you could take all that from one page, whole microwave, whole one. If I get any fraction, right? I'll be getting anybody about this up? Nah, that was big. Later will be more direct. There was one, and I can show you how the diffraction pattern is pretty. I'll look at, and I'm buying back, but I need it. I've missed doing that. Can we right here? Huh? In terms of, no, it's for that. Right, we take a little bit of the minimum there because we're gonna spend some time on, we're going to spend some time explaining this stuff. We come back to that. Push past, by here. And you another, Alex? Yeah, pass right here. Are you reading it? Take a little read, right? And this will give you the explanation. Explanation, real good. Sorry, taking long, I'm going to forget. Right, the next two parts are in the log test, so we're looking at the calculation. Right, it should look familiar to what we did in the for the interference. Should be familiar. All right, let's go take it too long. Probably, let's take it too long. Right, let's go. So the minima, right? So the minima are the points in between where we have lines, right? That's okay. So the minima is at X and Y. Right? Remember, this is central, right? This is central, right? And these are what? Smaller maximum, right? So the minima is just in the middle here. That's okay? Yeah? Kill it. It's followed up, Bishop. So we're trying to explain the minimum, right? So the minima, right? Or the minimum constructive or destructive with the parents. So right, would the minimum be max? Would the minimum be constructive interference or destructive interference? Minimum. That's these dark spots here. It will be destructive, right? So here on for destructive interference, the part difference is what? Destructive. Gotta look back for everything and then you don't understand anything. Analyze. Destructive interference is what? Part differences, half number of wavelengths, right? So we might see that here in our note, right? So let's take a look at it. In figure physics. Okay. Right, in figure 26.5, that's underneath here. AB is a slit of width E. You'll see enough? What's AB? And that whole width there, that whole thing there is small e. I can wait. Just say I'm there. I didn't hear that come back now. Here, I'll say that. Right? Consider now, make sure you all follow what's going on here. So you have A. So from the letter A to the letter B, that separation there is small a. Right? Now we're going to split up small a into 2n. Right? So we have 2n slits in there. Equal section. So therefore, you'll see that every width is a on 2n. If this whole thing is a, if this whole thing is a, and we divide it by 2n, then each of the widths will be this value here. Think about it. If the length is a, and we split it in 3, and each one will be a divided by 3. So if we divide it into 2n, each one will be a over 2n. Okay? Right, here's what it said now. Consider some direction theta to the normal. So imagine the ray coming in like that. This is the normal, and this is the angle theta here. That's okay? Pay attention, right? So again, lose us not any point times the top, right? consider some direction theta to the normal, and suppose that that lambda is the wavelength of the light being used. So the light here is lambda. That's okay? Right. So here what it's saying. If theta is such that AN is lambda 2, what does that indicate? Let's go back to our diagram. Where is AN? I'm zooming in here. You all see AN? AN is there. What does AN represent, Alexis? What's the word? Two words. What does AN represent? A light leaving, a ray leaving A and a ray leaving C. What does AN represent? Two words, one beginning with P and one beginning with D. Huh? Path difference. So the path difference for this way and this way is that distance here, AN. You see enough? Right, and Aaron, the question said that AN is equal to lambda 2. What does that mean when these rays meet? What does that mean? The path difference is lambda 2. What does that mean? What does that mean? What would happen at that point? And what happens at that point? Path difference is lambda 2. They will have this destructive interference, so they will cancel out in. Right? So if the path difference is that, they will cancel out wherever they meet. Okay? And that's what the note we're going to say. It says that if theta is such that AN is lambda 2, the wave at A will be completely out of phase with that of C. Okay? And the waves at A and C, will destroy each other when they come together at P, and hence the presence of Coulomb. When you're wrong with it. Page 453, 454. You just follow what's going on so far, Vanessa? So if you look here at that point P, they will have that destructive interference in. Okay, so that explains the minimum, right? Well, comes in the page with the calculation. 454 now, right? Hold on, Right. So here's what is said now. The lens does not affect the phase difference of A and C, right? That's the little lens in the middle. Let's pick up on the next page. You'll see a lens in the middle. It does not affect the phase difference of A and C. Similarly, light from each point between A and C will be destroyed by that from the corresponding C and D and so on. The same is true for every other pair, such as DE and EF. Therefore, there is no diffracted light in those directions theta, which is such that AN is lambda. That makes sense? Once the path difference is lambda 2, everything will be destructive. Again, we explain in the minimum. All right? Right, so watch this here. You can also go back and watch the diagram. AN is lambda 2, and they show you how to get AN. Use the right angle, and you will see that AN is AC sine ACN. Right? You might remember this, right? But from simple geometry, ACN and theta. Remember, I told you when theta is small, sine theta to theta, right? So now look at what happens to the formula. AC becomes AN 2n sine theta lambda 2. Right? If you were to rearrange the formula, you will get A sine theta is equal to n lambda. Right? These two will cancel, and the n will come here, and you will get A sine theta n lambda. So we can prove the formula using the minima as well. As well as we can prove it using the maximum. So the formula for diffraction grating is this. A sine theta and lambda. Theta is the angle it makes with the normal. A is the separation of the slits. N is the whichever fringe it's on, and lambda is the wavelength. That's okay. That's the first application. I don't know if you all recognize it, but this proof is just like the proof that we did for Y is the lambda. It's very, very similar. Okay, it's very similar. Right, so remember that it will work on either side of the normal. I'll show you that just now. Remember that E is much smaller, much bigger than lambda, right? Normal thing. Right, remember we said that opening has to be much bigger than the wavelength or comparable, right? Remember that? So if the opening real small, right? If the opening real small, those little things will happen, right? All right, so that's the first part of it. The next part, let's see if we can explain the central maxima. Can you all kind of envision? Can you all kind of envision why the central maxima is produced? What you will see the main thing, Vanessa. Why the center? No, without reading. Why I think the central max, the minima are being produced by the path difference being half wavelengths, right? So why that central maxima being produced? Right, but central maxima as a result of what? The path difference being what? Center, one in the center. The others are yes, whole number of wavelengths. So if the path difference is a whole number of wavelengths, the other maxima that is smaller intensities will be produced. But why or what do you think is the explanation for the central, right? What's the path difference say? Path difference is what? Anybody? Okay, let me just mumble again. Zero. The path difference at the center is zero. Okay? And all the others will be lambda and then 2 lambda and so on. Alright? So let's see what it said. In figure 26.6, all the waves arriving at home at any one point in time will have left the various points at the wavefronts A, B. What do you expect to follow? Watch it. Just watch it. Right? Will have left the series, sorry, the various points on the wavefront at A, B at the same time as each other. Since all these waves are in phase with each other, when they leave A, B, they are still in phase when they reach O. In making this statement, we are again relying on the fact that the presence of the lens does not affect the phase difference, right? But there's a little lens in the middle, right? But we are ignoring that. Thus, at O, the radiation from each point on A, B enhances that from every other, and therefore there's a brightness at O. Right? That makes sense? They all enhance each other, right? And then on page 455, I don't have that. Right? And they said the position of other maxima are difficult to determine, but the points listed below are worth noting, right? So here's what important about them, right? The subsidiary maxima are much less intense than the central maxima. We saw that in the diagram, right? Because O is the only point at which waves from each point of the wavefront interfere constructively with those from every other. The subsidiary maxima lie approximately midway between minima. Right? The width of the central maximum is twice that of each of the subsidiary maxima. Again, when they talk about subsidiary maximum, go back to page 453 and you will see the intensity diagram, right? Central right is the maximum, all the others are minimum. You're seeing that one of the highest, that's the max central max, and all the others are the central and the all the others are the subsidiary maximum. Okay, all right, right. So everything we just did, right, goes towards trying to explain the actual diffraction rate, right? So page 455 and 456 are the two most important pages. 455 and 456. Let me try now. After lunch. I want to give it that. Let's give it that first try now. That is 5 minutes. And then after lunch, we read again and we try to re-explain it. This is the most important thing. Right? I want to do it while something in your head. By the time you watch things on food and all kind of things, what's that called? Right? Last thing, diffraction grating. A diffraction grating is an arrangement of identically equally spaced diffraction elements, right? So as I was telling Vanessa, pitch here 1 centimeter here, and pitch here on that 1 centimeter, you have 1,000 spaces. So you can imagine how small it is, right? So 1 centimeter, right? And on that 1 centimeter, you have 1,000 spaces. Right? One of those is E. One of those. Right? That's how small it is, right? A diffraction variable. Normally, it consists of a large number of parallel lines of equal width ruled on a glass. So you have a glass and you take a cutter and cut it. Right? A transmission grating or metal, right? In each case, the diffracted elements are the clear spaces between the rulings. There are typically 600 lines per millimeter. That's an example, right? Diffraction gratings are used to produce optical potential. Figure 26.7 represents the section of a transmission diffraction grating, which is being illuminated normally by light of wavelength lamp. In everything, we are seeing D. Can we see D there? Don't put them here watching up there. So they don't want to buy it lost. Yeah, no, it's not. I have to explain it in more way. Yeah, you have to focus. You have to start your attention. Span of it to be 15 seconds. Right? So every 15 seconds, lock back in again. Reboot, shake it up, and lock back in again. All right? Right? Real quick, last thing. Each of the spaces A, B, C, and so on act like very narrow slits. That makes sense? Each one a narrow slit. And diffracts the incident light to an appreciable extent in all forward directions. Consider that light, which is diffracted at some angle theta to the normal, right? So we consider the light at that angle theta. So all those rays there, those 3 rays that are coming out, that's bending downwards, all at an angle theta, right? The slits are equally spaced, and therefore, if theta is such that light from A is in phase with that from B, it is also in phase with that from every other slit. So all these fellas here in phase, all of them, all 3 of them they're in phase. That's okay, right? It follows that light from each slit is in phase with that from each other. This happens whenever A n is what? What would A and B? A whole number of wavelengths. That's okay? So look at the formula and you will see that A n is D is equal to n lambda. Everybody okay with that? And if we do a little bit of maths, a real little bit of maths, we will see, watch it good. Watch good, right? D is the separation between the slits. You'll see what D is. D is not the opening. D is the separation between the slits. And if I do a little bit of maths, I can see that sine theta is equal to opposite, which is En over hypotenuse, which is 2. You'll see that? So what does that mean? It means that En is equal to D sine theta. Right? And remember all them in phase. All them in phase. So En is equal to n lambda. So now n lambda is equal to D sine theta. That's okay? That's what we had to understand. So you think you can redraw this diagram and explain how D sine n lambda? Right? Where the n lambda coming from again, Aaron? Why is it n lambda? Aaron, answer this, we done. How we going to break? Yeah, why is n lambda? Why is En equals n lambda? Why is En, but En again? Why is En equals n lambda? En is the what? What's En? Represents, you remember. Okay, why is En exactly what's En? En is what? The what? What's En? The path difference. Remember we showed the diagram, the little extra? En is the path difference. Why is the path difference? N lambda here. Come on, whole class is better than here. Why is En equals n lambda? Why is En equals n lambda? Alexis, because I want to get something else. Phase is what? They all have the same phase, right? So it means that if they all have the same phase, then the path difference will be what? A whole number of wavelengths because it'll be constructed, right? Right? It's still on the board, right? It's still on the board here. If it's constructive, means they're all in phase, so therefore the path difference n lambda. N could be 0, n could be 1, n could be 2. That's okay? You know what's the problem too? You have none of this written down and you're not trying to make sense like it. Yeah, but you gotta make sense like it. You gotta watch it and make sense like it. Right? We'll take a break at 15 minutes. Go class, sit down and try to make sense of all of it. So that's what to read right now in that one. Okay? Try to make sense of it. Be honest with you, this book is in good explanation for somebody. That's why read this book on your own, you might make more sense why you get it work. That's why you have to work more like right? You can just take pictures. This book, you want to this thing to understand push-ups. I just log out the Zoom. Oh,